Sometimes in class, I'll write that something is a fact. This is usually a statement that I'm not going to prove, but it is true, and I'll often want you to use it to prove something else. So for example, here's a fact. Let z be an integer, and let p be a prime number. Then if p divides z squared, it implies that p divides z. And by divides, I mean divides evenly. For example, 3 divides 27, but 4 does not divide 15 evenly. Okay, so again, take any z that's an integer, square it. The fact is, if p divides z squared, then p divides z. Okay. So I'm not going to prove it. One proof uses the fact that every integer can be uniquely factored into products of primes, but I don't want to get into that. So I'm just going to say, take this on faith that it's true, and I'll let you use it if you want to prove any other interesting theorem. Well, what theorem are we going to prove using this fact? We're going to prove the following theorem. We're going to prove that the square root of 3 is irrational. Now remember, in a previous video we already proved that square root of 2 is irrational. And what I'm going to do is mimic the proof that square root of 2 is irrational for square root of 3. I'm going to try and use the same proof, and you'll see that at some point I need to use this fact that if p divides z squared, then p divides z, where p is a prime number. This is an example of what your book calls adapting existing proofs. Namely, we already have a proof that root 2 is irrational, so if we want to prove that root 3 is irrational, let's try and adapt that proof and make just a few changes. So remember, we'd like to prove that the theorem is that the square root of 3 is irrational. Remember, it's a proof by contradiction, or at least that's how the square root of 2 case went. Okay, so we'll assume that square root of 3, we'll assume that square root of 3 is rational, and arrive at a contradiction. What does it mean for the square root of 3 to be rational? This means that root 3 can be written in the form a over b, where b is non-zero, and a and b contain no common factors, so it's in reduced form. Okay, so if the square root of 3 is rational, remember this is a proof by contradiction, then root 3 equals a over b. The next step will be to square, so we'll have 3 equals a squared over b squared. And this implies that 3b squared is equal to a squared. So you can see that 3 here is a factor of a squared, right? 3 divides a squared. So 3 divides a squared. Now by the fact from the previous slide, since 3 is prime and it divides a value a squared, this implies that 3 divides a. Okay, if 3 divides a, it means that a can be written as the form 3 times k for some integer k. This means that 3b squared equals, now I'm substituting 3k in for a, equals 9k squared. And this implies that b squared equals 3 times k squared. I divided both sides by 3 of this equation. Okay, so from here, b squared equals 3 times k squared. It means that 3 is a factor of b squared. Well, if 3 is a factor of b squared, by that fact from the previous slide, it means that 3 divides b. Again, 3 is prime. And now we've arrived at a contradiction. Why? Well, 3 divides a, and 3 divides b. But that contradicts the fact that a and b share no common factors. We assumed that square root of 3 was written as a divided by b, where neither a nor b shared a common factor. Here we've concluded that both a and b have the factor 3. So this is a contradiction, and it completes the proof. Now granted, it does use this fact from the previous slide that we didn't prove, so it's a proof assuming that one fact that I allowed you to use. And we'll see that over and over again. I'll let you use certain facts, and I'm interested to see if you can prove things based on those facts. Hopefully later in the course, we'll see why that fact is true.